So I wanted to talk a little bit more about diffusion by doing a couple of example problems. So you have a material at 300 degrees Celsius. You're given the diffusion coefficient at T1, which is 300 degrees, is 7.8 times 10 to the negative 11 meters squared per second. And the activation energy for diffusion is 41.5 kilojoules per mole. Okay, you find D2, where the temperature is 350 degrees Celsius. Okay, go ahead and work on this, and then we'll go over the answers you get. And you can raise your hand once you have the answer. I'll write it on the board. I can show you how I approach the problem. So D equals, we know this equation. If we don't have this number, right? We don't have D0. So, but I know it's a constant. So I can move this equation so I set everything equal to D0. So if I do that, I get, so far so good. Okay? And if D0 is constant, then I know that D1 I'm trying to solve for D2. I have this number, the temperature. I can look up R, it's a gas constant, and D1. So I should be able to solve for D2, right? I have everything I need. So if I do some algebra, this is not the only way to solve the problem, but that's how I approached it. And if you plug everything in, what do you find for D2? Meters squared per second? Yeah. And you want to make an N-type semiconductor. And we will talk about in this class later how to do that, like what that means, why you do the doping that you do. But basically, to make an N-type semiconductor, you start with pure silicon, and you add impurities. And the impurities you can add by several different ways, but one of the ways that people still use to add impurities is by diffusion. So you want to dope. So doping is adding impurities that you want. Dope silicon with phosphorus. And you want to add a concentration of 1 times 10 to the 21 atoms per meter squared. So the concentration of phosphorus you want at 1 times 10 to the 21 per meter cubed. So the way you do this is you use an inert gas, so nitrogen or argon, something that doesn't really react as a carrier for your phosphorus. And you use phosphine. Phosphine is pH3 as your source of phosphorus. So you put phosphine into a carrier gas, and you flow that across your semiconductor. And you have a wafer thickness of around 800 micron. And you want to dope your material. So you want to get a concentration of 1 times 10 to the 21 phosphorus per centimeter cubed at 80 micron. You can assume that you made your silicon wafer very, very pure, so your starting concentration of phosphorus equals 0, and that you're going to maintain your source, your gas source over your wafer at a constant. So that's not going to change. Okay, so you have a constant source of phosphor over the semiconductor. For this system, you have these values. The activation energy is 2.74 eV per atom. And D0 for the system is 8 times 10 to the negative 4 centimeter squared per second. And in order for this value to be true, these two values to be true, the temperature is in between 810 and 1,100 degrees Celsius. Okay, so this is what you know. The company has given you all this information because they've been making semiconductors for a long time and they know how to do that. But your company is trying to become more energy efficient. Sustainability, to be a better, more responsible manufacturer. So your boss wants to know, which is more energy efficient? To do the doping at a lower temperature, 900. So would you expect a lower temperature to take a longer or shorter time to get the same doping concentration? Longer. Or you could raise the temperature to 1,000 degrees Celsius, and you'll have a shorter diffusion time. So that's your job as an engineer, is to make a recommendation to your boss. Squared. Okay, make a recommendation to your boss whether you should be doping at 900 degrees Celsius or 1,000. So how would you approach this problem, you think? What would you be solving for here, if anything? Okay, so you want to know the time. You want to know how much shorter or how much longer are we talking about? Right? If it's 1 minute longer, seems like 900 would be great. If it only takes a minute longer to heat at a lower temperature. Or if it's a lot longer, then maybe you need to consult the manufacturer of the furnace to see how much energy it takes per minute to heat the furnace at 100 degrees higher and see if that makes any sense in terms of time, right? So you need to find the time. What equation do we know that can give you the time of diffusion? Does anyone know the equation? What does it look like? We have this equation, right? And we have all of the information that we need here. We already have the diffusion coefficient. We're given that. Well, actually, no, we're not given that, but we're given enough information to calculate for that. We are given Cx. Cx is 1 times 10 to the 21. C0 is 0. We don't know Cs, but we know it's constant. We have X. We have enough information to find D, and so forth. What can I say about this side of the equation? Is this constant, or is it going to change when I change my temperature? Constant, because the amount of phosphorus inside my material is not going to change. My starting surface concentration is not going to change because I'm keeping that constant. As an engineer, you have control over that. And we still want the diffusion concentration to be 1 times 10 to the 21 at 80 micron depth, regardless of temperature. Right, so we know that this is constant. So I can set this side of the equation, and actually I can, well, okay, I'll just do it this way. So 1 minus d1 t1, right? This is at 900 C, should be equal to 1 minus error function of x over 2 d2 t2. Because both of them are equal to the same constant. So I know that I could get rid of the 1, right? And for this value, the error function of whatever it is, to be equal to the error function of this value, the thing inside the error function must be equal. Okay? The x's go away, the 2's go away, and I could get rid of the square root. So I get d1, d2 equals t2, t1. Or d1, t1 equals d2, t2, and then I just move the d's and the t's around. Right? Okay, now can you tell me what is T2 over T1? Anyone have a ratio for T2 over T1? Did anyone get anything different? Okay, that's the number I got also. So we could say that T1, it's roughly equal to 9 times T2, right? So if we were to heat at 1,000 degrees for 1 hour, so that would be T2, that would mean at 900 degrees C, we need to heat the same wafer for 9 hours. So what do you think is more energy efficient? Without knowing the furnace, how much it costs to increase the temperature by 100 degrees, what would you guess? That's what my guess would be also. Of course, you would need to, if you were an engineer working, you would need to double check the energy consumption requirements for that furnace to operate at 900 versus 1,000 degrees. But 9 hours is a long time, 9 times. So if this were a 2-hour, right, time required, then this would be 18 hours. I mean, it's a big difference, 9 times. And so my guess as well is that it would be better to heat at the highest temperature you can, which is, a little under 1100, at the shortest amount of time possible, because the difference in time based on a small temperature change is so big. So if, different set of conditions, if we were to hold T constant, temperature constant. So let's say we decide we want to heat at 1,000 degrees C. And T1 equals 1 hour. Now we want to double the amount of time it takes. We want to double the amount of time, and we want to know how much further in to the material, the wafer, will our dopants diffuse. So how will X change? We're still looking at a concentration at X of 1 times 10 to the 21 atoms per meter squared. We're still looking at the same initial conditions and the surface concentration. Everything is still the same. But we want to know how much deeper into the wafer will my dopants go, right? I want to see how my X will change. So you could do this equation and calculate, plug in the D and then plug in the T and then calculate for the X with this whole equation. Or we just established that whenever we hold this side constant, the material in here, this ratio stays constant. Right? In order for this side to be constant, the ratio inside here has to be constant. And since we are holding this constant, so we know that X over 2 dt equals constant. So that means X1 over 2 dt1 equals X2 over 2 dt2. So if you double the time, what will happen to your distance? Will it increase or decrease? Should increase, right? But by how much? By the square root of 2, right? So by recognizing this, if this is constant, then everything inside here has to be constant. It gives you a shortcut in terms of calculating for the relationship between X, D, and T. You can, of course, always go back to this full equation and calculate through that, but you don't have to, as long as this is constant. And a lot of times when you are doing diffusion experiments, you can control this to be constant. All right? Then I'll see you tomorrow.